Okay, thank you so much for your patience. There's always some technical difficulties. My name is Roxana Shafiee. I'm really excited to be here with my European colleagues. I'm actually on a different time zone at the moment. I'm speaking from Boston. I managed to catch some of the talks, but I'm sorry I couldn't make it up at 3 a.m. to speak about hydrogen. Things haven't gotten that bad over here yet. So this is a bit more of an American perspective. But many of the things that I'm going to talk about today apply to Europe, and I'll be happy to exchange notes. The work that I'm about to present is published. You can scan the QR code and get access to the study. But that doesn't mean that it's, a closed chapter, and I'd be happy to talk more about how this project can be developed in the future. So actually, the story today starts with something that we teach here to Harvard undergraduates. So I find this framework to be really helpful when we think about how we're going to address the challenge of decarbonizing society. And by and large, the two first steps of decarbonizing our society, decarbonizing the electricity sector, and electrifying as many end uses as possible is largely underway. So we've seen that there's been an explosion in the use of renewables, solar and wind, and we see that many end users are starting to switch to electricity where it's possible through heat pumps or EVs. Now, it starts to become a bit more challenging when we think about what we're going to do for those end users which can't necessarily be electrified, where it's not technically feasible or it's prohibitively expensive. And as we are all here to examine, many people are optimistic about the potential of hydrogen to fill this gap for these hard to abate sectors that represents around 30% of greenhouse gas emissions globally. So across the world, there's been around $680 billion US dollars invested into hydrogen projects. These are all across the world and vary in their scope in terms of their intended end uses. But the main investments tend to be in Europe and the US, where there have been strong policy incentives to encourage hydrogen projects. So for instance, over here in the US, it's been through the Inflation Reduction Act, which was passed by the former President Biden in 2022, and the bipartisan infrastructure law, which is also passed to appropriate $8 billion in grants for the hydrogen hubs. Now, most of this focus has been on, as we have all heard over the course of this morning, on renewable hydrogen. So making use of the low-cost renewables that have gained prominence to turn water into hydrogen gas and oxygen, which can then, the hydrogen being used for a large range of end-use sectors. I don't need to explain this too much to this group. Now, while production costs are high, many reports and studies are optimistic that these production costs in the next 2 decades, by 2050, will drop dramatically, such that by 2050, hydrogen will provide low-cost abatement opportunities across a range of end-use sectors, ranging from passenger vehicles to industrial heating, to power generation. So this plot, what I'm showing you here, is a marginal abatement cost curve from Bloomberg, which is essentially predicting that by 2050, hydrogen will provide low-cost abatement opportunities, so abatement less than $200 per ton in many end-use sectors in the United States. But there's a problem here. And this problem, in order to really understand it, we need to go to California. Now, in California, there are around a few thousand light-duty passenger vehicles using hydrogen that registered in the state. And if you have one of these vehicles, then you'll need to go to one of these very flashy refueling stations in order to fill up your vehicle. Now, at the moment, the price to fill up your vehicles with hydrogen, with gray hydrogen in California, is around $16 to $25 a gallon equivalent. So it's, if we make that conversion. However, to produce that hydrogen, that gray fossil-based hydrogen, is only $1 per gallon. So what's going on here? Now, of course, as California, there are taxes involved, but production costs, the point here is that production costs are only one component of the delivered price of hydrogen. So we all know this, that not only do you need to produce hydrogen, using your renewables, it also needs to be stored and distributed before it's finally delivered to its final end use. And there's something else, is that different end uses will have different storage and distribution requirements dependent on the economies of scale and different seasonality needed for storage. So this means that one storage and distribution costs will not apply to all end uses. So many studies, when they consider storage and distribution costs across different end uses, will apply a fixed storage and distribution cost, not necessarily considering how different end uses will use these different sorts of infrastructure. So to give you an example, an industrial plant might be able to will have a large demand, say for instance of around 50,000 tons per day. These are just, exemplary figures. Whereas a smaller refueling station will have a much smaller distributed demand, which will impact the costs that they pay to distribute hydrogen. And again, to give you an example from the storage perspective, what I'm showing you here is natural gas consumption twice a year for the power and industrial sectors in the United States. And what you can see is that, especially for the power sector, there's a strong seasonality in demand, which indicates to us that there'll be a need for seasonal storage. But these costs are typically not captured in estimates of production costs of green hydrogen. And we know that these costs can be significant. For instance, the cost of on a per kilogram basis of storing green hydrogen or hydrogen in general increases significantly with storage length as you're utilizing your capital at a lower rate. So in our study that was published in Joule at the end of last year, we set out to ask in the United States, what is in the current delivered price of green hydrogen by end-use sector, looking at end-use sectors where electrification is prohibitively expensive or not possible, but not looking at these end-use sectors like light-duty freight or heating, where it's likely that electrification is going to be the dominant pathway for decarbonization. So we looked at pathways where hydrogen was really one of the only options to decarbonize, if not the only. So sectors like ammonia, refining, industrial heat, power, heavy-duty road freight. So our approach in the absence of being able to use empirical data was to compile data that calculated production, storage, and distribution costs across a wide range of assumptions, and using figures from that compiled data which reflected each end user's storage and distribution requirements. So for instance, it would not be appropriate to use storage and distribution costs for some end use sectors which were rates which represented highly utilized capital, when it was clear that some sectors would require seasonal storage, which would lower the utilization rate of, for instance, storage capital. And then we created an average of the aggregated data to gain an average delivered price in the United States for each end use sector. And then our next question was to ask, to cast this in terms of carbon abatement, to ask what is the carbon abatement cost of using green hydrogen in the United States across different sectors at these delivered prices. And in order to be able to calculate these delivered prices, we did draw on empirical data of current fossil fuel prices, and we made some assumptions about the efficiencies of fossil fuel systems compared to hydrogen-based systems in order to be able to make this calculation. Now, to spare you some of the more boring details, this is all outlined in the paper, and I'd be happy to talk about the methodological details a bit offline if you were interested. So now what I'm showing you is a first figure. Now, sorry, it's come out a bit blurry, but you can get the main gist, where we asked what is the current delivered price of green hydrogen by end use sector. Now, of course, we're calculating this in the absence of empirical data. Now, we calculated that the green hydrogen delivered price ranges from around $7 per kilogram up to $15 per kilogram, where storage and distribution adds on average $3 per kilo, but up to $10 per kilogram, for instance, in the road freight sectors. And what we see here is that the mobility sector has the highest delivered price, and this is usually just the low economies of scale because of the low distributed demand, means that it raises distribution costs, and that the power sector we find has the lowest distribution costs because of the economies of scale that can be achieved through distribution, but higher storage costs, and that's really because of that seasonal element needed for storage. So what does all this mean in terms of carbon abatement costs? So now I'm showing you those same end-use sectors, so ammonia, refining, steel, road freight, power, industrial heat. And now I'm showing you the carbon abatement costs. So this is how much it costs to use green hydrogen to abate the incumbent fossil fuels in those sectors, whether that be natural gas, grey hydrogen, or diesel. And in all instances, we looked at the carbon abatement costs exceed $500 per ton in each end-use sectors, taking those average delivered prices and also encompassing the error on that delivered price. And what I'm showing you here in the red, if you squint, is the carbon price in California. So this really indicates that the current abatement cost of using green hydrogen in the sectors is prohibitively expensive when we cast it in terms of any sort of willingness to pay for a decarbonization or a clean strategy. So now the next obvious question would be to ask, okay, well, will these costs decline? So there is the implicit assumption that in many of these analyses that with increasing deployment of electrolyzers, that these capital costs will come down over time, which will drive down overall costs. But of course, as I've demonstrated here, production costs are just one part of the supply chain. And we discussed this a bit more in length in a blog that we published on the Harvard website recently, thinking about will these costs decline? And really, there's kind of two things to take away here. The first is that when we think about where the costs will decline, when we think about production cost, is that, as we all know, is that the bulk of the production cost, if you're utilizing your electrolyzer capital at a high rate, is electricity. And as we're seeing in many countries in the US and in Europe, is that grid electricity prices, they continue to increase. So the question here is that, well, can we take hydrogen off grid in the United States? And many have proposed that, okay, well, if electrolyzers come down enough in cost, then we can run them at a lower capacity factor and still be able to make cheap hydrogen. But here's the thing, that if we're only running our electrolyzer capacity at 20 to 30%, well, then you're only running your storage capacity at 20 to 30% or your distribution. So those low capacity factors then affect other parts of the supply chain, which raise costs. And then you have the problem of storage and distribution costs. So as we all know, we've been storing and distributing hydrogen for a long time, and these technologies are relatively mature, and that in many instances, the high costs across different end uses are because of end-use specific lower economies of scale. So the potential for lowered storage and distribution costs are really called into question. So what does this all mean? So even if with storage and distribution, even if production costs decrease to $2 per kilogram, which is the target for many of these models, our analyses show that even if we reduce production costs to $2 per kilogram, abatement costs still exceed $250 per ton in many end-use sectors in the United States, even with a reduction in production costs. And this is assuming that those storage and distribution costs remain the same. So what do we take away from this? So we don't take away the fact that hydrogen does not have a future at all. And there may be some sectors where hydrogen is the only option, but the high abatement costs of green hydrogen, both in the currently and potentially in the future, even with strong cost reductions, suggests that the opportunities in the United States for hydrogen will be limited. But there may be some sectors where hydrogen really is the only option. And if we're serious about reducing the cost in those sectors, then it would be incumbent for us to invest in a broader range of storage and distribution technologies where we can lower the capital cost to lower the overall delivered price. But this early stage of decarbonization, investing so heavily into hydrogen when it's not clear that it's going to provide necessarily scalable pathway, is not a prudent strategy, and it would be a better strategy for governments, well, the US governments at federal and state levels, to invest in a broader range of decarbonization strategy at much earlier stages of technology readiness in order to make sure that this energy transition doesn't raise costs unnecessarily. So with that, I'd like to give some thanks to the colleagues across different centers at Harvard and invite any questions and discussions. Thank you so much.
Thank you so much. Interesting to see the challenge with having both low production cost and low storage and distribution costs, among other things. So we have some questions here in the chat. So for ammonia production, you identify low abatement cost. How does this depend on the assumed cost of natural gas as a counterfactual?
Yeah, absolutely. I mean, it's the other side of the equation, the cost of natural gas. So if the cost of natural gas increases, then the abatement cost should be lowered. And that's essentially why the equation in Europe is a bit different, because the costs of natural gas are higher. But we did the calculation that even if, and I think ammonia in Europe is the kind of lowest hanging fruit, the abatement costs, if you account for the fact that natural gas is more expensive in Europe, abatement costs for ammonia in Europe come to around $100 per ton. So a lot more feasible. But once you start looking at those other end use sectors where the differential in cost is a lot higher, like industrial heat or power, those abatement costs become above any sort of willingness to pay.
So connected to that is maybe the second question. So how sensitive are the abatement cost results to assumption on the capacity factor of electrolyzer across different sectors?
Yeah, really interesting. So the capacity factor is really interesting, but not necessarily for the electrolyzer, which a lot of studies have focused on, but rather for the storage. So we find that storage capacity is really important because it's all capex dominated, right? So if it's all capex, then your overall delivered price is really sensitive to those changes, whereas production cost is OPEX dominated. So it's a different equation. So we're trying to bring attention to the fact that, look, even though production is OPEX dominated, the other parts of the supply chain are CapEx dominated. So it's really they're really sensitive to capacity factors too.
Sorry, Salma, can I interrupt for a moment? I think there is one question. Paul, would you like to speak? I think you raised your hand for a question.
Yeah, sure, Stathis, thank you. And thanks, Roxana, for a nice talk. Earlier on, you put up a Bloomberg slide, and maybe it went by too quickly for me, but it looked like it was kind of a ranked marginal abatement cost plot, and then road freight was down in the lower left, and it looked like that was the lowest cost, which seems kind of opposite what your conclusions are. And I don't disagree with your conclusions. I'm just wondering what the difference between your results. Why did Bloomberg come up with such a low cost compared to these other sectors?
Yes, so here they're really assuming they're making the most optimistic assumption for the efficiency of fuel cells, really, so that you have the lowest carbon abatement opportunities because you have this efficiency benefit of having a fuel cell as opposed to an internal combustion engine. So the reason that
they're looking at the end use piece of the problem as well, not just the supply. Is that the difference then?
No, so we're looking at the end use piece too, but here they're looking at, so here the assumption is they're just looking at production costs, and actually the underpinning assumption for this marginal abatement cost here is that the delivered price is $1 per kilogram. So not only are they assuming a much lower delivered price, they're also assuming a really high efficiency of fuel cells, which hasn't been demonstrated commercially yet. So you have a lot of compounding factors, but the main reason that they get such low abatement costs is because of a delivered price, and why they have specifically low abatement costs for the transport sector is because they have really optimistic assumptions about fuel cell efficiencies.
Okay, good. Thank you.
No worries.